Hey everyone, back with question 8, and we are doing a cubic function. This is question 8 of paper 2020, math paper 1. Okay, so we're given the graph of g of x, which is equal to ax cubed plus bx squared plus cx, and a cubic function having the y-intercept at 0, as you can see in our graph over there, is drawn below. The coordinates of the turning point of G are minus 1 and 2. Yeah, makes sense. Remember your cubic function, 2 turning points. And we can see our first one's at minus 1 and our second one's at 2. Okay, first question. It says, for which values of x will G increase? Okay, so if we look at our graph over here, we can see that it's decreasing since it's coming from positive infinity of in the y, and it's decreasing and it continues to decrease, and then it stops at the turning point. So from minus 1 over there, it is now stationary. It's not increasing or decreasing, and then after it turns, that's what we define a turning point as. So it's decreasing at the turning point, it then starts increasing, and you can see that there's a positive gradient over here, so it's increasing all the way until our next turning point, and then it starts decreasing once again, and then going all the way to negative infinity. So for which values of x will G be increasing? It will then be increasing from minus 1 to 2. So it's the x values where x is greater than minus 1 and less than 2. Straightforward, easy 2 marks. Okay. Then 8.2 says write down the coordinates of the point of inflection of G. So our point of inflection is, if we're still looking at our increasing and decreasing, it is where we're looking at its acceleration at this point. So you can see that it's decreasing at this point, but it kind of starts slowing down. So it's still decreasing, but it's slower, and then it stops, and then it's increasing. So then at the point of inflection, which is halfway between our turning points, which is about there, we can see that it's still increasing, but it's not increasing as fast. So it's basically slowing down, and then once here it will then stop and then go and then decrease again. So it's very similar to acceleration in physics. So that's also why it's your second derivative. But so they're saying to write down the coordinates, okay? And since we know that the point of inflection is the midpoint between minus 1 and 2, we can simply just calculate the middle. And so to get the middle, we'll say x is equal to, we'll take our 2 points, we'll take the sum of them, so it'll be minus 1 plus 2 divided by 2, and this is a method you use all the time when trying to find the midpoint between two spots. So for example, if I had the number 5 and I had the number 75, and I asked you to calculate the midpoint between these two numbers, you would just add them together, and that will give you 80, and then you divide 80 by 2, and then this is 40. So even without having to memorize it and try and count, you can just say that the midpoint or the middle number between these two numbers are 40. Cool. Let's take that away. And yeah, so if we type this into our calculator, or you can do it yourselves, it's minus 1 plus 2 is 1, and this is a half, which fits our graph about perfectly. So this should be half over there. 8.3, for which values of x will G be concave down? So concave down would be everywhere on this side over here. So you can see that the inside of the curve is in a downward direction, where as on the left side of it you can see it's kind of upward. So we're looking at this concave down, and this is true from our point of inflection, which is half, all the way to negative infinity. So our answer is simply where x is greater than a half, or our point of inflection. Yeah, it's pretty quick and easy. Okay, 8.4, it says if g prime of x, or the first derivative, is equal to minus 6x squared plus 6x plus 12, determine the equation of g. Okay, so from the beginning they didn't tell us what g is, and so we can simply just work our way backwards or find the integral of it. But yeah, I don't think grade 12's covered that yet. So what we'll do is we'll say g of x, using our g prime, we'll just undo the power method. So this first term over here, it's x squared, but we know that if we undo the power method, it's going to be 2 plus 1, the same way that you would normally minus 1. And then this minus 6 over here, instead of multiplying it by our exponent, we'll be dividing by exponent, but we want this when this number is complete, so we know it's 2 plus 1, which is 3. And then we'll do the same thing for the next two terms. So we have x, this is to the 1, but we know it's going to be 1 plus 1, which is 2, and then we'll divide 6 over here by 2, which is the result over there. And then with 12, we know that we just have to, we'll end up with a x over there, so like that. And of course, if you were doing some integrals, you would add a constant, but from our original equation, you can see that there's no d, so we can just tell that that is 0. And let me just simplify this. So g of x is equal to minus 6 divided by 3 is just minus 2x, and then 2 plus 1 is 3, plus 6 divided by 2 is 3x, and then 1 plus 1 is 2, and then our 12 is just x over there, because if you have to use a power rule on this, you can see that this will then be 1 minus 1, which is 0, so this term becomes 0, and you just leave for the 12, so we like undoing that. Okay, and then from here we have our g of x. You could see that if you have to compare this to what they're asking, our a value would be minus 2, our b value would be 3, and our c value would be 12, and we determined our g of x. Coolio. 8.5, and it's the last question. Determine the equation of the tangent of g that has a maximum gradient. Write your answer in the form of y equals mx plus c. We know that's a straight line. So maximum gradient, if we go back to our graph over here, the maximum gradient we have is at the point of inflection. The same thing with the acceleration. This is where the acceleration is at its highest. So the maximum gradient, I'm just using mg to say maximum gradient, is at x is equal to a half. That is our point of inflection, remember? So what we'll do is we'll take this and we'll substitute it into our formula of our first derivative, which is this over here. So we'll say that g prime of a half is equal to minus 6 of a half squared plus 6 of a half multiplied by half plus 12. We can then type all of this in our calculator. I feel like I said that a lot this series. And if we type all of this in our calculator, we are ending up with 27 over 2. Okay, or in other words, our gradient is equal to 27 over 2. Okay, with this value, so we have our m value, we have our x value because we know it's at this point, and so we just need our y value. And to get our y value, we will substitute our x into our original equation, which is g over half which equals to this over here, which is minus 2 half cubed plus 3x, oops, not x, half squared plus 12 times a half. And once again, all of this goes into calculator and you'll get an answer of 13 over 2. So we got a one set of coordinates, which is x equal to a half and y equals to 13 over 2, and we got a m value as our gradient. We can then solve for our straight line to get it in this form. And to do that, we'll take y minus y for our coordinate is equal to m, which is our gradient, x, what we're looking for, minus x, our coordinate that we have. So y we just leave as is, minus the y that we have, which is 13 over 2. It's equal to our gradient, which we have as 27 over 2, x what we're looking for, and the x of our coordinate that we have is a half. We then simplify from here. So we have y, and then we'll take the 13 over 2 over, and we'll multiply this in, so it becomes 27 over 2x minus 27 over 4, and this becomes plus 13 over 2, and then y equals to 27 over 2 is the same as 13.5x. You can leave it in that form. I don't think the form matters that much. Minus, and then this way I have to simplify. Of course, you can type this in your calculator. This becomes 26 over 4. Oh, that's a minus, so it's 1 over 4, which is just 0.25. Cool. And that is question 8. Thanks for watching, guys. I'll see you in the next one.